Chapter 15, Waves. Waves cover waves, wave on a stretched string, wave equation, interference of waves, standing wave, and resonance. You can find them in the timeline. Waves and particles. Particle and a wave are the two great concepts in classical physics, in the sense that we seem able to associate almost every branch of the subject with one or the other. The two concepts are quite different. The word particle suggests a tiny concentrate of matter capable of transmitting energy. The word wave suggests just the opposite, namely a broad distribution of energy filling the space through which it passes. The job at hand is to put aside particles for a while and to learn something about waves. Types of waves. Waves are of three main types. 1. Mechanical waves. All these waves have certain central features. They are governed by Newton's law, and they can exist only within a material medium, such as water, air, and rock. 2. Electromagnetic waves. These waves are less familiar, but I use them constantly. Common examples include visible and ultraviolet light, radio and television waves, microwaves, X-rays, and radar rays. These waves require no material medium to exist. Light waves from stars, for example, travel through the vacuum of space to reach us. All electromagnetic waves travel through a vacuum at the same speed c. c equals 299,792,458 meters per square. They are governed by Maxwell equations. 3. Matter waves. Although these waves are commonly used in modern technology, their types is probably very unfamiliar to you. Electrons, protons, and other fundamental particles, and even atoms and molecules travel as waves, because we commonly think of these things as constituting matter. These waves are called matter waves. They are governed by quantum physics. Much of what we discuss in this chapter applies to waves of all kinds. However, for specific examples, we shall refer to mechanical waves. Transverse and longitudinal waves. Look at this picture. A guy is operating with hand up and down in one direction, and we see a wave passing through to the positive x direction. The displacement of every such oscillating string elements, y, is perpendicular to the direction of the travel of the wave, such as in this figure. Okay. This motion is said to be transverse, and the wave is said to be a transverse wave. Now look at this is an element vibration along y direction, which is perpendicular to the direction of the wave transmit. Look at this one. This is sun. The guys pull force back and forth. Okay, we see the sun transmit in the air, and the molecule of air vibrate along the direction of the air wave. The vibration of the element of the air, the dot, are parallel to the direction of the propagation. The motion is said to be longitudinal, and the wave is said to be a longitudinal wave. Both a transverse wave and a longitudinal wave are said to be traveling waves because the wave travels from one point to other, as from one end of the string to other end, or from one end of a pipe to the other end. Know that it is the wave that moves between the 2 points, and not the material, string or air, through which the wave moves. Wavelength and frequency. For a sinusoidal wave, like that in figure B, okay, traveling towards increasing value of x, the transverse displacement y of a string element at the position x at time t is given by yxt equals ym sine kx minus omega t. Here, ym is the amplitude of the wave. That's the maximum displacement. The subscript m stands for maximum because the amplitude is the magnitude of the maximum displacement of the spring element in either direction, parallel to y direction. Now, this is magnitude. Okay. Hence, ym is always positive quantity. Okay, that's definition. Okay. This is y at x and t. We call it displacement at time t at location x of the element of medium. Ym, as we say, the maximum displacement is always positive. We call it amplitude. Okay. Sine, you have an angle. We call it, this sine we call it phase. And k, we call it angular wave number. X is the position. T is time. And omega we call it angular frequency. These kx minus omega t sine we call the phase. The quantity kx minus omega t is called the phase of a wave. Y at xt equals ym sine kx minus omega t. This is a propagation wave. Okay. This is amplitude ym. This is a phase. If we look at this, this is a wave propagation along the x direction. At the one instant, it's this way. We look at this point. Okay. But later we find it goes to x, and this is a repeat. We call lambda. That we'll talk about it later. Okay. It can repeat, repeat, and repeat. Okay, this is the shortest repeat unit. Another time it's go this way. Another time it's go. So we see the wave move towards the positive x direction. And look at this. Okay, at this point x, at this moment it's this amplitude displacement maximum, and at this moment it go this one. At this moment it go down. It is just so this point is going up and go down when the wave move. Let's look at another one. Another one at the beginning is 0, and then it go down, and then it go back and go up and go down. So it moves up and down, up and down, and we will see that the maximum displacement for those points are the same. This is the ym. You may wonder why of infinity variable of waveforms that are available, we pick up the sinusoidal wave for detailed study. This is in fact a wise choice because all waves formed, including the paths, can be constructed by adding sinusoidal waves of carefully select amplitudes and the value of omega. So understanding sinusoidal wave is thus the key to understanding the waves of any shape. Now, this is y at t, ym sine of t. So we see y is function of x or t. Okay, or we can write this one. So we study this way, we have two ways, because you have x and t, two variables. So we take x as constant. So we standing there, watch the motion of the element of medium. Also, we can take t is constant, and we look at different x, okay, so that we can watch the waveform. At different point, it has different displacement. Wavelength and angular wave number. What are the wavelengths? Look at this wavelength. This is x, this is t. So we look at it at the same t. Suppose that t equal to 0. T can be any one number, okay? Suppose t equal to 0, this kind of a wave. We look at this wavelength. Wavelength lambda of the wave is the distance along the direction of the wave, x, between repetitions of the wave shape. They repeat it again and again. This is the shortest repetition unit. Or we take 2 lambda, it repeats. 3 lambda, it repeats. We take the shortest lambda, okay? So, what does this mean in mathematics? Mathematics is y at the same time, x1, this one, y, equal to y, x plus number, x plus number, this is x1 plus number here, repeat it. This y is the same as this y. So this is mathematics. This is mathematics. We look at this. Y at xt equal to ym sine of t. So we take t equal to 0. T can take any point. At any point, x1, the yx1 is for this one, ym sine kxx1. This is a t. And of t, x1 plus lambda equal to ym for this one, at kx1 plus lambda. This is a t, 0. And we, by definition, the lambda, yx1 equal to yx1 plus lambda. And so this one equal to this one. Okay? We write ym sine x1 equal to ym sine kx1. We compare these two. Ym cancel out. So the phase inside must be same or a little bit different. What are different? Okay, kx equal to kx1 plus k lambda. So k lambda by trigonometry, k lambda must be equal to 2 pi or 2 pi, 3 pi, 2 pi plus m. Since we take the shortest repetition, so we take m equal to 1. K lambda equal to 2 pi. Or in this case, we will find the k, we call the angular wave number. Okay? Because in the angular, sine, this is the angular. Angular wave number, k. In metric system, this is called radial, this is radial, over meter, lambda is meter. K equal to 2 pi over lambda, or lambda equal to 2 pi over k. We know lambda, we know k, we know k, we know lambda. Period, angular frequency, and the frequency. At any position x, we fix that. We watch it, the more vibration of the element of medium, okay? And for example, we take x equal to 0. X can any position, and we watch the vibration. This is time t, not xt. At the same x, so its vibration we record and plot it. What is the period? Period, we define the period of oscillation t of a wave to be the time interval between repetitions of the motion of an oscillation string element. I would say that the shortest repetition, okay? So, what does this mean? Mathematics, y at x is 0 time t, t1, this is y at x equal to t1 equal to y x is the same 0. T plus t, this is a t plus t. This is a period. The y are the same. We can take any x that means different point. We get a definition. The same reason, you see, yxt equal ym sine kx minus omega t. And we take x equal to 0 at time t, y t1 equal to, this is a t1, this is 0 minus omega t. And y0 t plus period t, we put this one, t plus period t. This is 0 minus t. Since definition of the period, y0 t1 equal to y0 t1 plus t. This is minimal representation, okay? So we put this one inside. So we get this one is ym sine minus omega t equal to this one, ym sine minus omega t. We compare this equation, we find, okay, minus omega t1, minus omega t1. So minus omega period must be an integral number of 2 pi. It can be 2 pi, 3 pi, n 2 pi. Since we take the minimum, so we'll take n equal to 1. So omega t equal to 2 pi. Then we know the period equal to 2 pi of omega, or omega equal to 2 pi over t. The omega is called the angular frequency. This is the frequency in the angle, the sine angle, angular frequency of the wave. Its metric system unit is called radius over time second. Okay. T equal to 2 pi over n, or omega equal to 2 pi over t. The frequency f of the wave is defined as 1 over t. Okay, so once we know omega t or frequency f, one of them, we can find another 2. So omega is called angular frequency. How do I remember? This is frequency. 2 pi is the angle. So the angle frequency is omega. Speed of an travel wave. We look at this wave move, okay, from the beginning, the green line, to this brown line, okay, with velocity v. So what we do, we see at that time interval delta t, it moves delta x, and its velocity is delta x over delta t, or dx dt. How do we find this one? The wave is traveling in the direction of increasing x to the right of the figure. The entire wave pattern moves a distance delta x in that direction during the interval delta t. The ratio delta x over delta t, or in differentiate limit dx dt, is the wave speed v. How can we find a v? We can take a different reference point. For example, from this point to this point, from this point to this point, the delta x are the same in the same period, right? So we look at this. How can we find the velocity? Okay, now this is the wave. Okay, we look at this too. We find the particular part of a wave pattern. The phase, the same phase, the same y. So we take the phase is constant, okay? Phase is constant. Different phase, for this is the one phase, okay? No matter what constant it is. For example, we can take this phase, we can get this phase, different constant. So at the same time t, it moves the same distance, okay? The issue in physics, in math, we take this phase, it's constant. What the difference, the phase constant means x and t combination different, okay? At time t1, x is here. At plus delta t x here. Anyway, this is constant. So in this case, we can find dx dt. We do the derivative on both sides. This is k dx dt minus omega equal is constant. So dx dt equal to omega over k. Okay? When we know omega t is 2 pi, k lambda 2 pi, we put this one, we get equal to lambda over t. And then 1 over t is f. Okay? So we have the velocity of the propagation wave v equal to lambda f equal to omega over t equal to lambda over t. One of them, omega t or f, you can find the other two. Now, how do you remember this one? Let me remember this one. What is velocity? By definition, velocity is the distance traveled in unit time, called velocity, right? So dx dt. Yeah. Okay? For example, 1 second. 1 second, how many distance it travel? We say, in 1 second, it repeats 3 times. That's the definition of frequency. And each time it moves a wavelength lambda. So V equal to F lambda. This is the way I remember that one. Okay? The wave speed is the distance traveled in 1 second. And in 1 second, the wave repeat F time. Repeat F time. And each time you travel a wavelength. So V equal to lambda F. In 1 second, the wave oscillates F frequency cycle. Each cycle has wavelength lambda long. This is how do you remember this velocity of the propaganda longitudinal wave?
On this wave machine, long rods are attached to a square wire spine at regular intervals. If we tip the first rod, a torsion wave travels down the spine. This wave machine is identical to the first, except that the rods are shorter. A wave travels faster on this machine than on the other one.
Okay, yxt equal to ym is kx minus omega t. Wave travel along positive x direction because this is minus, we will prove it. Okay. We have another one. Another one is positive. This is negative. This is the wave travel along negative x-axis. Why? From here, constant, okay? We do the derivative on both sides. We get a k dx equal to, let's see, we get a k dx plus omega 0. So v equal to minus omega over k equal to minus lambda over t equal to minus f lambda. It is propagated along negative x-axis. Traveling waves must be informed xt is kx plus minus omega t. This is a linear relationship combination, okay? So this is a xt is a linear combination. It is possible a travel wave. And this is not, because this is square. It's not a linear relationship, okay? Sample. A wave traveling along a string. It's described by this one. We have this one, ym. This is the k, omega, in which the number constants are in metric system. This is meter, this is radian per meter, and this radian per second. Okay? What is the amplitude of this wave? This is one. Okay? So y equal to 0.00323. This is a meter unit. Okay, or equivalent to 3.27 millimeter. Question B, what are the wavelength period and frequency of this wave? This wave, we know K, 72.1. we know k lambda is 2 pi. So we know k, we know omega. Okay. What is the lambda? Lambda is k lambda equal to 2 pi. So lambda equal to 2 pi over k. We get this one. Okay. Yeah. Frequency equal to 1 over t. A period, okay, what is period? Period equal to 2 pi over omega, right? So we put this omega in, we have this omega, we get a frequency. What is the period of this, or what is the velocity of this wave? With the velocity, make this one derivative with the time t. We get velocity equal to omega over k. We know omega, we know k. We get a 3.77 centimeter per second. Okay. What is the displacement x? Sorry, displacement y at x 22.5 centimeter and t 18.9 centimeter. Very simple. We put xt inside, we get y. We see in this formula, okay, we get a lot of information, okay. The amplitude, the lambda, the k, angular wave number, and the omega, and from omega we get a period, from k we get a lambda, okay. Remember, k x 2 pi, omega t 2 pi. Sample. In the above sample, we show that at t 18.9 seconds, the transverse displacement y of the element of the string at x 0.225 meter due to the wave is 1.92 meter. Okay? Question A. What is u, the transverse velocity of the same element of the string at that time? Remember, this is the speed of the element of the spring. So it's along the y direction, okay? Okay, wrong direction. Do not confuse it with v. There's different v. V is the wave velocity, while u is the velocity of the element of the string. Okay? So we know this y. This is the displacement of the element of the string. What is velocity? dy dt, or round y round t. Okay? We do this one with respect time to time t. We get a minus, we get omega out. So we get du t equal to, we take this minus out, and sine becomes cosine and y. Okay? So we put the number in sine. We get omega, we get the ym, we get a k, we get the x, we get the omega, we get a t. That's elementary mathematics. I'm going to do it. Question B. What is the transverse acceleration A of the same element at the time t? This is acceleration of the element of the string, not the wave. Okay? This wave is traveling uniform speed. Okay? So this A is second derivative round x round t. Okay? Is round u round t. We could do this one around t again. So cosine becomes minus sine. You have another minus, so you get a 3 minus omega sine. And originally you have minus, so you get a minus omega squared. Okay? That's squared. Okay. Finally, A is minus omega squared y. You look at this one, what do you find? You find A proportional to its displacement. So this is a simple harmonic motion, okay, with frequency omega. Wave on a stretched string. If a wave is to travel through a medium such as water, air, steel, or a stretched string, it must cause the particles of that medium to oscillate as it passes. For that to happen, the medium must possess both inertia so that kinetic energy can be stored and elasticity so that potential energy can be stored. These two properties determine how fast the wave can travel in the medium. And conversely, it should be possible to calculate the speed of the wave through the medium in terms of these properties.
We can send a wave pulse down this rubber tube by jerking sharply on the free end. Notice the propagation speed of the wave. If we increase the tension of the rubber tubing by stretching it, how will the wave speed be affected? The wave speed increases. Further increasing the tension will even further increase the speed of the wave.
V equals square root tau over mu. This is we have been proved. Okay. The speed of a wave along a stretched ideal string depends only on the characteristics of the string, tau and mu, and not on the frequency of the wave f, which is fixed entirely by whatever generates the wave. The wavelength of the wave along the string is fixed by lambda equals v over f. The f is decided by the source, v decided by the medium, and then we get the lambda. Wave speed v on a stretched string. Derivative from Newton's second law. An ideal string is there are no friction-like forces to cause the wave to die out as it travels along. Wave equation. As a wave passing through any elements on the stretched string, the element moves perpendicularly to the wave's direction of travel. We are dealing with a transverse wave. By applying Newton's second law to the element's motion, we can derive a general differential equation called the wave equation that governs the travel of waves of any type. We know this one is vertically up and down, but the vibration oscillate, okay? And the string is almost horizontal direction. We look at this section of element in the string, okay, with length dx. It was exert two forces, a 2n, this is F1, this is F2, okay, and it will have acceleration AY up and down, okay, no direction movement along x direction. So this one move up and down because F2y along y direction minus F1y equal to sigma f equal to ma. M is dm, this one. A is ay, okay? F equal to ma. Now we find F2y, Ft1, okay? And dm equal to length multiplied by mu. This is a mass density, right? This A equal to second derivative of y respect to time t. Now we find F2y and F1y. Look at this one. We look at this tau. This tau is F2, okay? And F2 can be looked at F2x squared plus F2y squared square root. And we see the string is almost horizontal, so F2y is much smaller than F2x. So we can approximately think F2 equal to tau equal to F2x. Okay. And also we see the ratio F2y to F2 is this angle, tangent theta. This tangent in mathematics is derivative of this curve, dy dx at this point, point 2. Okay, so with these two helps, we get F2y equal to F2 tangent theta. Okay, F2x tangent theta. And tangent theta equal to this one, dy at point 2. And F2x equal to tau. So we get approximately, we see F2y equal to tau times tangent theta at this point. Okay. Similar, we can see F1y equal to tau dy dx at point 1. And then we see the F equal to ma. F2y minus F2y equal to ma. This is a tau, put this side. Tau dy dt point 2 and tau dy dx point 1 equal to m mu dx 8. Second derivative of y with respect to time t. All right. Okay, with this approximation, we see that one. This is the formula, we just got it. And look at this point. We can take the tau out. This is a dy dt x point 2. This is dy dt x point 1. So we can call this one where d, the change, dy dx. Okay, this is g, the differentiation. Okay, d. And we see this with dx, we move this x over here. So this becomes dy dx dx. This is second derivative, okay, and move tau to here, mu over tau dy dt. And rewrite this one as a v because equal to tau over mu square root. So mu over tau equal to 1 over v squared. We rewrite this one, we get, this one is 1 over mu squared. We put everything inside, we get y second derivative with respect to time x equal to v1 equal to 1 over v squared and second derivative round y round x for t. This equation, how I remember this one, we see that x equal to vt. Yeah. So I put this one, can easily remember. Okay, and this equation called a wave equation, apply to many wave situation. Remember that in the previous section we have this one, the traveling wave. You put this aside, it satisfies the equation. And this one, velocity v equal to omega. Interference of waves. Principles of superposition for waves. It often happens that two or more than two waves passing simultaneously through the same region. When we listen to a concert, for example, sounds from many instruments fall simultaneously on our eardrums. The electrons in the antennas of our radio and TV receivers are set in motion by a whole array of signals from the different broadcasting centers. Y equal to y1 plus y2. We consider only 2. Okay. Overlapping waves algebraically add to produce a result wave. This is another example of a principle of superposition, which says that when several effects occur simultaneously, their net effect is the sum of the individual effects. The principle holds as long as the amplitude of the waves are not too large in acoustic, optics, electromagnetism, quantum physics. Amplitude are not too much. Look at the two waves. They meet together. Okay, one from left to right, one from right to left. They intercourses and they separate again. Moreover, Each pulse moves through the other, as if the other were not present. Overlapping waves do not in any way alter the travel of each other.
Here is a torsion wave of medium amplitude traveling left to right. Here is a wave of the same amplitude traveling right to left. We'll now send these waves in simultaneously to show what happens when they meet. The amplitudes add as the waves pass through each other. Then the waves continue on their way unchanged. Here is a torsion wave of medium amplitude traveling left to right. Here is a wave of the same amplitude traveling right to left. We'll now send these waves in simultaneously to show what happens when they meet. The amplitudes add as the waves pass through each other. Then the waves continue on their way unchanged. What will happen if the waves have equal but opposite amplitudes? The waves cancel momentarily, then pass on. This demonstration uses an Apple computer-based real-time spectrum analyzer consisting of a series of filters covering the entire 10-octave audio spectrum in 1/3 octave intervals. To indicate the calibration, the cursor will now be moved from 100 Hz up to 10 kHz with an audio oscillator set to each frequency. The top channel shows the total intensity of the signal. Using this analyzer, we can observe the groups of harmonics, called formants, associated with certain sung vocal sounds. Here is a male voice singing the vowel oo at a frequency of about 150 Hz. The frequency of the first formant is about 300 Hz, and the frequency of the second formant is about 800 Hz, so they overlap. Here is a male voice singing the vowel E at a frequency of about 150 Hz. The frequency of the first formant is about 300 Hz, as in the vowel OO, but the frequency of the second formant has risen to about 2500 Hz. The difference between the sounds OO and E is the frequency of the second formant. The second formant does not change significantly as the frequency of the voice changes for the same vowel sound.
Fourier analysis. French mathematician Fourier explained how the principle of superposition can be used to analyze non-sinusoidal waveforms. He shows that any waveform can be represented as a sum of a large number of sinusoidal waves of carefully chosen frequencies and amplitudes. Fourier's theorems tell us that every curve, no matter what its nature may be, or in what way it was originally obtained, can be exactly reproduced by superposing a sufficient number of simple harmonic curves. Okay. In brief, every curve can be built up by piling up waves. You can see now why we spend so much time analyzing the behavior of a sinusoidal wave. When we understood that, Fourier's theorem will open the door to all other wave shapes. Now, this is almost like trigonometrical wave. Okay, it can be looked at as so many sinusoidal wave together. Okay, and written it can be written as minus sine omega t over pi, minus sine 2 omega t over 2 pi, minus sine 3 omega t over theta, and so on.
This Fourier synthesizer produces electrical signals of precise frequencies. It produces a fundamental frequency of 440 Hz. It can also produce harmonics of the fundamental at 880 Hz, 1320 Hz, 1760 Hz, and higher frequencies. We can select harmonics to add to the fundamental with amplitudes and phases we choose. The sum of all the signals we select are displayed on this oscilloscope and speaker. Here is the fundamental at 440 Hz. We'll now add the second harmonic at 880 Hz. Notice how the sound changes. Now we'll take away the second harmonic and add the third at 1320 Hz. Here is the fundamental with the ninth harmonic at 3960 Hz. Now we'll add together a specific combination of fundamental and harmonics to make a square wave. Here is a different combination which makes a triangular wave.
Interference of waves. Suppose we send two sinusoidal waves of the same wavelength and amplitude in the same direction along a stretched string. The superposition principle applies. What resultant wave does it predict for the string? The resultant wave depends on the extent to which the waves are in phase, in step, with respect to each other. That is, how much one waveform is shifted from the other waveform. Now this is a one waveform shift from other waveform, okay? Yeah. We put them together, and we get this time the free. Actually, you can see look at some intensity. This is a positive, this is negative, and this is a little bit less. So the final resultant is this one at this point. This curve is made from this way, okay? They put them together. If the waves are exactly in phase, so that the peaks and the valleys of the one are exactly aligned with those of the other without any shift, these two are exactly overlapped, okay? And in this point, the amplitude is double, okay? This double, okay? Now, they combine to double the displacement of either wave acting alone. If they are exactly out of phase, the peak of the one are exactly aligned with the valleys of the other. Now, Okay, and then we see some instant exact the same, so 0. Say the resultant is 0. Okay, they cancel out everywhere, and the string remains straight. We call this phenomena of combining and cancelling of wave interference, and the waves are said to interfere. These terms refer only to the displacement of the waves. The travel of the waves is unaffected. They're going on, traveling, okay? Only affect displacement of the wave. So, suppose y1, this is the first wave, ym sine kx minus omega t, and y2, x2 is ym sine xt minus k plus phi. You see what? Compared to these waves, they have the same amplitude ym, same speed omega over k, same wavelength lambda, because k is the same. K lambda equal to 2 pi. K is the same, lambda is the same. Same frequency omega. So they have same period and same direction, because it's minus sign. Okay. But different phase constant phi. This is 0, this is phi. They're only that difference. And suppose they meet somewhere, we see the interference between them. Okay. Put them together, and the sum of them is the result. Let me do some exercise. Okay. We put y1, y2 inside. Okay. y1 equal to ym sine kx minus omega t. Okay. y2 is ym sine kx minus t. Okay. And then we have ym in comma. We take it out. Okay. We're getting sine alpha plus sine beta. Okay. We know sine alpha plus sine beta in trigonometry. Sine alpha plus sine beta equal to 2 sine half alpha plus beta cosine half alpha minus beta. We put this as alpha, this is a beta. So sine alpha to beta, okay, and divide by 2. So you have this one, kx minus omega t plus half theta. Okay, and the cosine, you minus this one 2, you get phi. Have 2. So the result is 2my cosine half phi sine kx minus t plus half f. The result. Let's look at the result wave. It is still a traveling wave with the same k, same omega, same direction, same velocity, a little bit different phase. And the amplitude changes. The amplitude changes depends on the phi. Okay. If phi is 0, they are in phase, in step. Cosine 0 is 1, so you get y equal to the maximum amplitude of 2y. If the phase is 180, and then we say cosine 90 degrees is 0, you get 0. Okay, that's called out of phase. Okay. Now, we have these two, we get this one. Let me re-emphasize it. This is the final component wave. It's still a traveling wave, okay? It's still traveling with the same velocity, the same lambda, or some frequency, a little bit different phi. But the amplitude changes, depends on the phase difference between these two, okay? See, okay? So maximum is 2m, minimum is 0, depends on the phi. If two sinusoidal waves on the same amplitude and wavelengths travel in the same direction along a stretched string, they interfere to produce a resultant sinusoidal wave traveling in that direction too. Okay. The resultant wave differs from the original waves in two respects. One, its phase constant is half phi. And two, Its amplitude y is 2ym cosine phi. Depends on the phase difference. Now, if phase difference is 0, they overlap. We get maximum. Okay? 2m. If phase difference is 180, then shift halfway, they don't see any vibration. So the phi is 180, y equal to 0. And we have a between. Okay, this is the propaganda transverse wave. Okay, with the same direction, same velocity, same wavelength, and so on, same frequency. Okay. Now, if phi equal to 0, cosine 0, 1, they reach the maximum value 2mv. Interfering that produce the greatest possible amplitude is called fully constructive interference, phi equal to 0. If phi equal to 180, cosine 90 degrees is 0. The y prime m is 0, and we see no motion of string. This type of interference is called fully destructive interference. Everything destructive. Okay. Know that when the interference is neither full destructive or nor full destructive, it is called intermediate interference. The amplitude of the resultant wave is then intermediate between 0 and 2ym. A phase difference phi equal to 2 pi radius corresponds to a shift of one wave relative to the other waves by a distance of one wavelength. So phase difference can also be described in terms of wavelengths. Now you look at this one. For example, this one too is shifted by 0.5 wavelengths, and they are out of phase. Okay. 2 pi phase difference equals 1 wavelength shift. Okay. So if they overlap, okay, the delta phi is 2 pi, or lambda is 1 lambda. So we can 2 pi phase difference equal to lambda shift. Okay, lambda change shift. Okay. That's very important. So in this case, two waves, their delta L equal to m lambda. 1 lambda, 2 lambda, 3 lambda shift phi. This one is m lambda plus half lambda. Okay, m can be 0, 1, 2, 3, 4. Shift, they are the same. Okay. Two waves with the same wavelength are in phase if their phase difference is 0 or any integral number of the wavelengths. Thus, the integral part of any phase difference expressed in wavelength may be discarded. For example, a phase difference of 0.40 wavelength is equivalent in every way to one of 2.40 wavelengths. And so, the simpler of the two numbers can be used in computations.
We'll use this ripple tank, which projects an image of waves on the surface of water, to show interference of waves from two closely spaced slits. When we put a pair of slits in front of the waves, an interference pattern results. Decreasing the wavelength increases the number of nodal lines in the pattern. This split-screen view shows the patterns resulting from the two wavelengths. Increasing the separation of the slits also increases the number of nodal lines. This split-screen view shows the patterns resulting from the two slit spacings.
Sample. Two identical sinusoidal waves moving in the same direction along a stretched string interferes with each other. The amplitude Ym of each wave is 9.8 millimeter, and the phase difference phi between them is 100 degrees. Question A. What is the amplitude Ym of the resultant wave due to the interference of these two waves? And what types of interference occurs? It's simple. We just put in the formula. Okay, Ym prime equal to 2Ym cosine phi. Okay, and the phi is 100 degrees, so we put Y. This is Ym is 9.8. When we put a number, we should use the standard unit, meter. So this is 0.0098 meter. We get Y prime. Okay, it's 0.013, 13 millimeter. Okay, getting a little bit larger. Okay, it is intermediate interference. Question B. What phase difference in radius and wavelengths will give the resultant wave an amplitude of 4.9 millimeter? We also use the formula. This one is 4.9 millimeter. It should be equal to this one. We want to find this phi. So we put in sign. Okay. We can find the cosine phi. Okay. Now, you have this one. We only pick up the one to suit our purpose. Okay. And then we put this one, the phase difference, and we put the lambda. So it's about 0.42 lambda. Okay. This is a phase difference 2.6 radio, equivalent to 0.42 lambda. Phasors. We can represent a string wave or any other types of wave vectorially with a phasor. In a sense, a phasor is a vector that has magnitude equal to the amplitude of the wave and that rotates around an origin. The angular speed of the phasor is equal to the angular frequency omega of the wave. Now we look at this one. This is a phasor, can represent a wave. Okay? And we define, in this book, we define counterclockwise is the positive direction omega. Okay? Now, look at this. Here is minus omega. Okay? So as the phasor rotates around the orange at angular speed omega, okay, its projection y on the vertical axis varies simultaneously from a maximum Ym, so 0, to a minimum of minus Ym. This variation corresponds to the sinusoidal variation in displacement Ym of any point along the string as a wave passing through it. Now, this one is go direction because it's minus omega. Positive direction, this one is minus, go this direction. And its projection on the vertical line is the y1. y1 equal to ym. This angle is called kx minus omega t. y, and 1, get this one. Okay. When two waves traveling along the same string in the same direction, we can represent them and their result wave in a phasor diagram. This is y1, okay, equal to y1m sine kx minus omega t. Okay, this is y1. Okay. And then we have y2. Y2 is y2m with the same direction, same wavelength, same frequency, only different phase. So this y2 is this one. This phase is positive number, is counterclockwise. So it faces this one. We put them together. And in phasor diagram, with this vector, okay, we put it E, the same vector, and we find the sum of these two, we get this one. This is y prime, the sum, resultant wave vector, okay? And it has a beta angle with the first one, okay? The first one is 0, okay? First one, okay? So what we do, we look at this one, because the E are the same. So this is equal to this one. So this beta angle equal to this beta angle. And this phi is what is? Phi is the angle between the first one and the second one. This is phi. Okay, that's phi. So which is that this is this y1 equal to y12 equal to ym. Then because the y with ym prime with the resultant y is what? So we take this from beta equal to half phi. Y1 is equal to 2 this line. Each this line equal to y1m cosine beta. So y1m equal to 2 ym cosine beta. Beta is half theta. Okay, and then we see the result are the same as we do in above calculation. Okay, so finally ym equal to ym prime. Okay, sine kx plus c. Exactly the same answer. This time we do from the Phasors, vector phasor. In case y1m equal to ym to y, beta equal to half theta, and we know the resultant was equal to Tym plus c, the amplitude. Okay, and you got this one, the answer. Okay, know that in contrast to the above methods, using Phasors allowed us to combine waves even if their amplitude are different. In above calculation, algebraically, we have required these two are the same, but with the Phasor, they cannot be. They can not different. Okay, I'm sorry. Know that in contrast to the above method, using Phasors allowed us to combine waves even if the amplitude are different. These can be different. Two solenoidal waves, y1 and y2, have the same wavelength and travel together in the same direction along the string. Their amplitude are y1m 4.0 millimeter and y2m 3.0 millimeter, and their phase constant are 0 and pi over 3, respectively. What are the amplitude ym prime and the phase constant beta of the resultant wave? Write the result wave. Now, this is a phasor, the vector. We treat them as a vector. Okay, we move the second one to here. We find the sum y1m. This is the resultant wave. Okay, this is 3 over the pi. How do we find? This is, as usual, we divide it into x direction, y direction. Okay, so y prime horizontal, y direction, equal to this horizontal, this cosine theta. Okay, this horizontal. Okay, and this one horizontal, y2m cosine pi. Okay, and we put the number inside. We take the millimeter as a result. Okay, and y vertical is, this vertical is 0. This 90 sine theta is 0, and this is a sine pi over 3. Okay, and we get this number. Once you get a two component, we get y. Ym is the square root of this and this square. Okay, we get the answer. And the angle is tangent beta equal to vertical of horizontal, y of x is 2.60 over 5c. We get the beta. So finally, we can find the answer equal to c. Y prime equal to magnitude 6.0 millimeter sine kx minus c plus 0.44 radius. That's it. Standing wave and resonance. Let's consider two sinusoidal waves. Y1 at xt equals ym sine kx minus omega t. Y2 at xt equals ym sine kx plus omega t. We look at these two waves. They have the same amplitude ym, the same wavelength lambda because k is the same frequency omega, same speed omega over k, but different direction of propaganda. Okay. Because of they go in different opposite directions, so there's no phase problem. Okay. Now we put these two together. When they interfere by the principle of superposition, the final y primes equal the sum of these two, and we put y sine kx minus omega t. This is ym kx plus omega t. And we take the km out, we get this km sine alpha plus sine beta. Alpha is kx minus omega t, beta is kx plus omega t. We know the equation of a trinomial formula. Sine alpha plus sine beta equals 2 sine half alpha plus beta cosine half alpha minus beta. We use this alpha beta, we get this one into 2ym sine kx cosine omega t. Oh, this is a result of interference of these two traveling waves. You see what happened? It is not traveling waves anymore, because traveling wave you need combination of x and t. So, but the particle of element, the string, vibrate as cosine omega t. The only difference is the amplitude, a different position, different x, we get a different amplitude. Okay. So what we call it? We call this a standing wave. It is a wave, but it's not traveling. It is a standing wave. We look at this. These two plus together, we get the displacement y prime equal to 2ym sine kx. This is called amplitude at position x. Cosine omega t is oscillation term. Okay, different x, they have different amplitude. Sometimes it's 0, sometimes maximum 2 am. If two sinusoidal waves of the same amplitude and wavelength travel in opposite direction along a stretched string, their interference with each other produces a standing wave. This is a standing wave. We look at the standing wave. At some moment, suppose there's two waves. One go to the positive direction, this one. One goes in negative direction. And we put them together with this green one. Let's see, after one course period, okay, so this one go 1/4 go to the end, okay, and this one from here you go to this one, okay, and this one we put together, we get a straight line. They are exactly opposite. And then we see another quarter period. So this 0 go to here, this 0 go to here, and this maximum go to here, okay? And we'll put these two, we get this kind of interference. And after another quarter period, this one go to here, and this one go to the nipper. So this one go to here, this one go to less. They are just opposite, so you get another this line. And we go another quarter period. This one go to this here, and this one go to the middle. So they put together, we repeat it, same thing. This is we call it standing wave. It does not move. It's not traveling. Okay, it's not traveling move. Okay, and it vibrates. Element of the string vibrates. The only thing is we see all these black points. Their amplitude is always equal to 0. Okay, and some other points, like this point, they have very big, large amplitude. Okay, and different point has different amplitude. Okay, now that's the one. The amplitude is different based on the location of x. Okay, this is called a standing wave. It's a wave. It's standing, not traveling. In a traveling simultaneous wave, the amplitude of the wave is the same for all string elements. This is not true for standing wave, in which the amplitude varies with position x. Okay. Let's see. The amplitude is 0 for the value kx. Satisfy this equation. Now, this equation we know kx equal to n half pi. N can be 0, 1, 2, 3, 4. Okay. So in this case, the amplitude is the maximum, or 0. Okay. We substitute k equal to 2 pi over lambda. We find x, the location is n half lambda. N can be 0, 1, 2, 3, 4. At this location, the amplitude of the wave is 0. Okay? As the position of 0 amplitude, we call it a nodes. Okay? For the standing wave, nodes, that adjacent nodes are separated by half lambda, half wavelength. Okay? If sine kx equal to plus or minus 1, and then we get a maximum amplitude 2 plus or minus 2ny. Okay, we make x to 1. We know kx equal to n plus half pi. N can be 0, 1, 2, 3. We replace k equal to 2 pi over lambda. We found the location of x is n plus half lambda. Okay, n can be 0, 1, 2. At this point, the amplitude is the maximum 2 mb. We call it antinodes of the standing wave. The antinodes are 1/2 wavelengths apart. If you look at this one, and one change one, you have to half pass. So the antinodes are 1/2 wavelengths apart, and the nodes are 1/2 wavelengths apart too. And the antinodes are located halfway between the pairs of nodes. And the nodes is located halfway between the antipads. That's very interesting. Okay, we look at this one. Okay, all these black points, their amplitude is 0. They are nodes. Their distance is half lambda. See, half lambda. And look at it, all these red points. At these points, at these points, their amplitude is largest. Largest, and their distance is half lambda. Between the two neighbor antinodes, you have a nodes. Between two neighbor nodes, you have antinodes. That's very interesting. This is standing wave.
If we send a wave pulse along this wave machine, it is reflected at the end. If we continue sending pulses at regular intervals and then adjust the frequency until it is just right, the incoming and reflected waves add to form a standing wave. Increasing the frequency slightly destroys the standing wave. Increasing the frequency even further to just the right value creates another standing wave with a shorter wavelength.
Three strings under different tensions will be used to demonstrate the effect of tension on standing wave formation. The ends of the strings hang over pulleys with weights of 0.9 Newton, 2 newtons, and 8 newtons providing the tensions. All three strings will be driven at the same frequency. Here are the three standing wave patterns produced. If we decrease the tension in the center string by lifting up on its weight, its standing wave pattern changes to match that of the lower string. If we increase the tension in the center string by pulling down on the weight, its standing wave pattern changes to match that of the upper string. We'll now show standing wave formation resulting from different driving frequencies. This rubber tube is put under tension by a weight hanging from the end. A beater strikes the end of the tubing at an adjustable frequency. At a very low frequency, the tubing hardly reacts. But as the frequency is raised, the fundamental of the tubing is excited and the amplitude increases greatly. If we increase the frequency, the fundamental disappears. As we continue to increase the frequency, we excite the second harmonic. We continue to raise the driving frequency and strike the third harmonic. Here are some of the higher harmonics in slow motion.
This device is used to demonstrate longitudinal waves, where the displacement of the medium is parallel to the motion of the wave. When the first rod is pushed sharply, springs between the rods pass the motion along. If the first rod is moved back and forth at certain frequencies, standing waves appear.
Reflection at a boundary. We can set up a standing wave in a stretched stream by allowing a traveling wave to be reflected from the far end of the stream, like this one. This boundary, this point is fixed. We call it hard reflection. Okay. In the figure, we used a single pass to show how such reflection takes place. Only single pass, cannot wait. Okay. This is another situation. At this end, it can move up and down. It's free. We call it soft reflection. This is hard reflection. The hard reflection, this point is fixed. The soft reflection at this end is flexible. Fixed far end, hard reflection. This point is fixed. When the pulse arrives at that end, it exerts an upward force on the support, the wall. By Newton's third law, the support exerts an equal but opposite force on the string, so it goes down. Okay. This reaction force generates a pulse at the supporting, which travels back along the street in a direction opposite that of the incident pulse, inverted by reflection. There must be a note at the supporting because the string is fixed here. Okay. The reflected and the incident pulse must have opposite sides so that it cancels each other at this point. So anyway, this point is fixed point. It's notes for standing wave.
When a wave pulse on a spring reaches the end of the spring, some or all of the wave is reflected. In this first case, the end of the spring is attached to a rod so that it can't move. Here's how a wave reflects from the end. We'll repeat that in slow motion. Notice that the reflected wave is an inverted version of the incoming wave. Now we'll tie the end of the spring to a long light string so that the end moves freely.
Software.
The wave now reflects without inverting. Let's compare the two types of reflection side by side.
Flexible far end, soft reflection. At this end, it can move up and down. So we see that when the incident pulse arrives, the ring moves up the rod. As the ring moves, it pulls on the spring, stretch the spring, and producing a reflecting pulse with the same sign and amplitude as the incident pulse, not inverted by reflection. Thus, in such a soft reflection, the incident and reflected pulse reinforce each other at this point, create an antinodes at the end of the string. The maximum displacement of the ring is twice the amplitude of either of these pulses.
We'll send a torsional wave down this wave machine to show what happens when the wave reaches the end. When the rod at the end is free to move, the wave reflects back with the same positive amplitude as the incoming wave. If we fasten the last rod on the machine so it can't move, the reflected wave has an amplitude opposite that of the incoming wave.
Standing wave and the resonance. Consider a string which is stretched between two clamps, separated by a fixed distance L. Like this one. So the traveling wave can back and forth on this force, so standing wave can be formed. Okay. We know that at this point, the fixed point, there must be nodes. So this is one of the possibilities that established the standing wave. After a force exerted on a stretched string, many harmonic motion take place at the beginning. You have a lot of frequency, back and forth, okay? The wave reflects at the fixed end and it travels leftwards, back force. The right-going wing and the left-going wing then interfere with each other. For those with frequencies other than the resonance frequencies, they will die out because the phases reflect at the end cannot match with each other. Sometimes cancellation, sometimes reinforcement. Only those resonance frequencies were built up because the reflected phase will reinforce the original one. For certain frequencies, the interference produces a standing wave pattern or oscillation mode with nodes and the large antinodes like those. Okay. These are nodes. So these are also one of the possibilities. This one, see, the length is half wavelength. This length is the one wavelength or two half wavelengths. This length is three half wavelengths, and so on. Such a standing wave is said to be produced at the resonance, and the string is said to resonate at these certain frequencies called resonance frequencies. This one, okay? If the string is oscillated at some frequencies other than a resonance frequency, a standing wave is not set up. Then the interference of the right-going wave and the left-going wave result in only small, perhaps imperceptible oscillations of the string. We look at this one. If this is air, these three are also the part of the possibility. We have a lot of possibility, okay? It looks so the air relation with the wavelength is air equal to n half wavelength. This is a 1/2 wavelength. This is a 2/2 wavelength. This is 3/2 wavelength, and so on. Okay. So in this case, wavelength lambda equal to 2L over n. N can be 1, 2, 3, 4, 5. Okay. And the frequency equal to mu over lambda. This mu, it depends on the stress. Square root tau over mu. This lambda we decided by this one. So we get a frequency. Frequency equal to mu over lambda. Lambda equal to 2L over n. We put this one, the frequency is n mu over 2L. In this case, the frequency is the multiple integral time of this number. Okay. Mu is depends on the stress stream. Okay. So n equal to 1 we call the fundamental frequency. N larger than 1 we call the harmonic frequency. Equation F equal to n mu over 2L tells us that the resonance frequencies are integral multiples of the lowest resonance frequency F equals mu over 2L, which corresponds to n equal to 1. The oscillation mode with the lowest frequency is called fundamental mode or the first harmonic. The second harmonic is the oscillation mode with n equal to 2. The third harmonic is that with n equal to 3, and so on. The frequencies associated with these modes are often labeled F1, F2, F3, NE1, N2, N3, and so on. The collection of all possible oscillation modes is called the harmonic series, and n is called the harmonic number, or the nth harmonic. Look at this. The phenomena of resonance is common to all oscillating systems and can occur in 2 dimensions and 3 dimensions. For example, this figure shows a 2-dimensional standing wave pattern on the oscillating head of kettle drum. Okay, these are notes. Okay, these are notes.
Have you ever wondered how the head of a drum vibrates when it is struck? We'll use this flexible rubber diaphragm and this speaker to show some of the forms of vibration. The speaker drives the rubber drum head with sound waves from beneath. Here is the fundamental vibration of the drum head seen with a strobe light to slow down the motion. Here is an oscillation at a higher frequency. Notice the circular nodal line. Here is a different type of oscillation with a nodal line running across the diameter.
In this demonstration, we will observe standing wave vibrations of an aluminum plate. An oscillator in the 10 to 30 kilohertz range produces sine waves which are amplified by this audio amplifier and fed into this small coil. A piece of thin-walled annealed nickel tube is mounted rigidly to this black anodized aluminum plate, and the tube is inserted into the coil. The process of magnetostriction in the nickel tube converts magnetic oscillations of the coil into mechanical vibrations. The frequency is set as shown by the inset at the lower left of the picture, and sand poured onto the plate. The sand illustrates the standing wave pattern by gathering along the nodal lines. Now the frequency is adjusted to show various standing waves in the plate. The wooden plates on a violin would exhibit this type of oscillation.
Sample. In the figure, a string tied a sinusoidal vibrator P and running over a supporting a Q is stretched by a block of mass M. The separation L between P and Q is 1.2 meter. Okay. The linear density mu of the string is 1.6 gram per meter, or 0.0016 kilogram per meter. The frequency F of the vibrator is fixed 120 Hertz. The amplitude of the motion at P is small enough for that point to be considered a note. A note also exists at P. So PQ is a note. We have 4 half lambda shows here. It's coefficient. Question A. What mass M allows the vibrator to set up the fourth harmonic on the string? Want to find M. Okay. Actually, it's the tension, right? Now we see the frequency F equal to N V over 2L. In this case, N equal to 4. 1 half lambda, 2 half lambda, 3 half lambda, 4. N equal to 4. Okay. And L is 1.2 meter given. The mu, okay, mu is the square root tau over mu. This tau is mg, okay, okay. This linear momentum, a linear density is given. So we put this one here. This is 120. We can find the tau, or the m, okay. We find m equal to 4L square F square mu over n square 2. We put the number inside, okay. L is 1.2 meter. Frequency is 120. Mu is meter, 0.0016 meter, kilogram per meter. N is 4, G is 9.4. Okay. Look at M. Question B. What standing wave mode is set up if M equal to 1.00 kilogram? Okay. Well, with M equal to this equation, we see what M is fine. We put also number inside, we find N. If M equal to 1.00 kilogram, N is 3.7. That means no resonance can set up, okay? No standing wave can be set up on the string. Next chapter, chapter 16, sound wave. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.